Hi, I'm Dan Piselli, Director of Sustainability at FX Collaborative Architects. With me today are Jeremy Shannon, Director of Sustainability for the New York City School Construction Authority, and Paula Zimin, Director of Sustainability at Stephen Winter Associates. Today we're talking to you about how we've used passive house principles and approaches to inform New York City public school design. Everybody's heard about Local Law 97. However, a lot of people criticize it because it doesn't apply to city-owned and operated buildings. However, those folks might be forgetting that the city is doing its own laws and regulations to limit its own energy use. One of those measures is Local Law 31 of 2016, which limits energy use in city-owned and operated buildings and is very aggressive. So this study applies, helps the New York City School Construction Authority achieve Local Law 31 of 2016. And we've used passive house approaches to get there.
Yeah, so thanks, Dan. We were excited to, when we first started thinking about at the New York City School Construction Authority about how we were going to comply with this Local Law 31. We were excited to have FX Collaborative and Stephen Winter Associates and the team that was assembled for that kind of get together and start working on how we were going to achieve this goal with our capital new schools. Many of you might not know, I didn't know until I started working at the SCA a number of years ago, that the SCA builds anywhere from 10 to 15 new schools every single year. So there's a really large impact on any sort of sustainability changes to new construction, even though New York City is a city of basically, many existing buildings. We're actually still finding spaces, amazingly enough, to build these 15 new schools each year. So what I have on the screen here is something to show you of all of the different local laws that we've been tracking that apply to sustainability for public schools. So in 2016, this Local Law 31 for the low energy intensity building law came about. And interestingly, in the draft of the legislation, it was titled kind of the Passive House Law, and it had referenced passive house multiple times throughout the law. And actually, New York Passive House was a strong advocate for pushing this to really help New York City buildings move forward on the city-owned side. And as a way of trying to make it so that it was non-proprietary or something like that, it was kind of shifted to become the low energy intensity building law. But let's just jump into now the, how we've tackled the Local Law 31.
So here's some brief highlights of Local Law 31. It applies to new city-owned and operated buildings. There are some compliance pathways that are near term and like term. So in the near term, there's kind of a choice to meet a Local Law 84 target, which is essentially 50% below the median source EUI for schools in the city. Or an ASHRAE compliance pathway, 50% below ASHRAE 90.1 2013. Whichever is less stringent is required by law. And then there's the 2030 goal of 38 kBtu per square foot per year, which is passive house. Our challenge was essentially to do both, to understand what minimal compliance meant and to understand if it was even possible today to achieve the 2030 goal with new schools. Additionally, we had to study solar energy. There's a requirement in Local Law 31 that 10% of the load has to be covered with photovoltaics. Okay, so here's the passive house criteria, 38 kBtu. The base case school that we looked at started at around 88.2 EUI. So that translates to 57% improvement. So we had our work cut out for us. Fortunately, the School Construction Authority had already tried very hard to make very good schools. They have a set of standards for normal schools But there already is a net zero school on Staten Island, where the SCA had tested many low energy building techniques. Unfortunately, that building is kind of in a suburban neighborhood. It uses many strategies that are not available to most schools in the city. For example, it has skylights and corridors because it's only a 2-story space, and you can have multi-height corridors with skylights. It has very deep shading devices that control solar gain. It has a huge photovoltaic array on the roof and over a parking lot. Those kinds of things are not available to buildings like the one on the right, which is near my office in the Union Square area, which faces north, is bounded on 3 sides by other buildings, and is 5 stories tall. While it's great that there's this net zero school, it's a great, it wasn't really, we weren't really able to use a lot of the lessons learned from it. So about the base case school that we looked at, it's in the Hunters Point South neighborhood, which is a totally new development that's in construction now. You can see here, it's this low building on the right image between those 2 taller towers. So it's essentially shaded out in the winter by one of those buildings. So it doesn't get that much solar gain, which is one of the passive house principles in the first place. Here's what it looks like. Basically a 4-story school, very simple, but quite elegant design. It's essentially an academic bar with a cafeteria and kitchen wing to the north. Here's the ground floor. Very simple layout. Pre-K and administration are in the bar part of the building here. The cafeteria and the kitchen are to the north. And then the upper floors have the rest of the academic wing program in that bar shape, and the gym is above the kitchen and cafeteria. Here's a section that just shows that basic layout. And here's the back. One of our challenges was to not change the design at all. Essentially, we were trying to figure out if we could make local law 31 happen for these schools, without compromising aesthetics. That was one of our main challenges, which I should say now that we essentially succeeded. Our design has virtually no aesthetic changes to the base case.
Okay, so when we started the study, as Dan sort of just mentioned, we had a base case school to start with, and if you're familiar, as Jeremy had earlier pointed out, there are already some green standards and that the SCA has implemented as part of their process. So since the 2000s, the SCA has developed the Green Schools Guide, and they also have to comply with Local Law 86, showing a good energy compliance in comparison to Energy Code. So this building that was already 100% designed came to us with an energy model already intact. The energy model was developed by the mechanical engineer, the designer of record, and it was compliant with the current version of the Green Schools Guide. So our first task really was to understand the process by which SCA standards tell design teams how to design and how to evaluate energy. And we grappled with, we took a look at the energy results, and we were really diving into and questioning what some of the basic assumptions were in that model. And then we used both the passive house design strategies. We used PHPP, the passive house planning package, to evaluate heating and cooling loads. And we also used the Energy Plus and OpenStudio plugin to help us evaluate mechanical systems a little bit better. On the next slide, we go into what specific questions we were asking. As you're familiar with passive house, obviously there's a focus on the actual performance of an envelope system. I think very often in the energy modeling world, which I work in on a day-to-day basis, we don't focus on actual energy performance of the envelope system as heavily as we do in the mechanical system, HVAC system world. So using the passive house planning package and the passive house strategies to evaluate derating and thermal bridging of envelope systems was a key component of how we're just going to get started. So we evaluated all of the traditional thermal bridges that would happen at a parapet, at the slabs, at the heated basement levels, and other small areas, which would be around each and every window, and mechanical system penetrations, as well as brick ties. So we really wanted to get a better idea of how this enclosure was actually performing. Were we accounting for people and equipment correctly, both in terms of quantity and in terms of scheduling? In terms of the thermostat set point, was it modeling standard the right guideline for thermostatic set points? And where is the fresh air going to come from? If we build tight and ventilate right, as the old adage goes, are we pulling from the right location? And then in the next slide, I wanted to show you some of the results of that investigation. Overall, we found that most of the enclosure systems were performing 30 to 40% worse than as they were modeled. So for example, the punched windows were modeled at a U factor of 0.45, but they were actually performing, because of the thermal bridging around the perimeter, at about 0.62 because of that thermal bridging. The walls were modeled as a U factor of 0.055, but they were actually performing at 0.071 when you factor in the thermal bridging, and so on and so forth. So when we decided to model that, and in the next slide we find out that the actual impact that all of that thermal bridging cumulatively will have to our heating and our cooling loads. We modeled this both in OpenStudio and in the Passive House Planning Package, because we also wanted to see how these two programs were valuing these thermal bridges. We see in the OpenStudio model, the heating load increased by 20% due to thermal bridging, and in the Passive House Planning Package, the heating load increased by over 30%. We will also note that the cooling load had a little bit of a change, but we do find that in dense urban buildings, the cooling load is not as impacted by these thermal bridging and small steps to improve the envelope as much as the heating load would be impacted by it. So how did this all play out? So what we basically did is we took the mechanical engineer's Green Schools Guide and code compliant energy model, and we refined it. We refined it to include these thermal bridges. We refined it to account for some systems that they may not have modeled, but they modeled a little bit differently. And as Dan had pointed out, we started out with a base case EUI of 88.2. And you notice in this bar graph, there is what I like to call the big green monster. Big green monster being the kitchen load and the plug loads combined are, almost 38 kBTU per square foot per year, and our 2030 goal is 38. So how are we going to bring this whole building down in terms of source EUI if we don't first address that big green wall, those internal loads that would otherwise be standards, and we wouldn't be able to get to our target. This is sort of the structure of how we approach the study as a whole. We did focus on plug load ECMs, tried to determine specifically what systems and equipment are going to be put into the school, and can we model them explicitly? We then evaluated kitchen ECMs. The kitchen represents one of the largest loads in the building. It's a commercial kitchen, has gas equipment, gas cooking equipment, has a servery, all the things that you would expect in an elementary school kitchen. Then we looked at lighting and elevator ECMs. You see that all of those are the internal loads we wanted to focus on first, because just in alignment with the passive house principles, we want to reduce all the internal loads of this building first before we balance them out with the external loads, the weather that the building is going to see, and the climate conditions, and balancing it within the enclosure. And then lastly, once we found a good balance, we addressed and investigated several HVAC systems and surface hot water strategies. So related to internal loads, as I said, the plug loads were one of the highest, and I think it was one of the more interesting not more interesting, the whole thing was interesting, but it was a very interesting part of the study to evaluate as Jeremy said earlier on in this presentation, SEA has it builds 10 to 15 schools a year, and because they are so prolific in development of the same building typology, they have a pretty strict standard that they require design teams to follow. But there's a lot of assumptions that go into energy modeling, and the standards that the SEA had set were based on standards that were about 10 years old. And those standards are a per square foot standard. And we said to SDA, well, why don't we do an accounting of all of the equipment that you typically put into buildings? And they have a very detailed list of all of the equipment that they would put into a second and third grade classroom versus a science room versus a computer room versus a gymnasium. They have some very detailed information that we could combine all together, apply different schedules to explicit equipment, and we were able to really reduce the plug loads just by accounting for the equipment explicitly. And then we were able to identify some other energy saving opportunities through converting from maybe laptops from desktops, specifying multifunction printers and Energy Star equipment in general. On the next slide, we just want to show that overall we were able to, just through accounting, reduce the plug loads by 30%. And then with these additional ECMs, we were able to reduce an additional 8% in terms of plug loads. The next thing that we had to look at was the kitchen and the kitchen systems. And this one was definitely a challenge and required a lot of collaboration, not just within our study group, but also for the SVA to reach out to their partners that operate the schools and operate the kitchens to get their feedback on some of the ideas that we were evaluating. One of the first things, again, similar to the plug loads, was just to do a full kitchen accounting to make sure that we were representing all systems and equipment correctly as they would actually operate within the kitchens. And then we were looking at demand control, ventilation, and other unique things that you would have in a commercial kitchen situation. I will say we also looked at just very simple things like food service menu changes. For example, this school is likely going to operate in the summertime, and an idea was floated out there that maybe one day a week they serve a cold sandwich lunch as opposed to, let's say, a hot soup lunch. And just changing the food service menu slightly can have a huge impact on energy use. Some of you may be familiar with a movement toward electrification as the ultimate goal to reduce greenhouse gas emissions related to fossil fuel use. So although the SDA didn't necessarily have a standard for fossil fuel kitchens, that was the most common new design that was put into new buildings. We did do an extensive evaluation of electric cooking, and we found that we were able to identify a way to switch over to electric cooking from gas cooking that has a slightly net positive greenhouse gas emission result. As we discussed, we already talked about maybe they go have a hot lunch program versus a cold lunch program and reduce our summer cooking. And there's also some opportunity for capturing some heat rejection off of a refrigeration system in the kitchen to maybe do some preheat of hot water in the kitchen. So this is the results of the carbon emission evaluation for a gas kitchen versus an electric kitchen. The gas kitchen, with the demand control ventilation being slightly higher than the demand control ventilation required for an electric kitchen. There's more pollutants that would need to be exhausted out of a gas kitchen than out of an electric kitchen. So the flow rates can be slightly different, and that combined with the electric kitchen system the electric kitchen has a lower greenhouse gas emission footprint. So then we go on to lighting, and our evaluation of lighting essentially revealed that the SDA has done a lot to date related to reducing lighting loads in their buildings. So there weren't easy opportunities to further reduce lighting. We'll go to the next slide, and we'll talk about the lower lighting levels. SDA had a foot candle requirement that was slightly higher than the Illuminating Engineering Society. And their recommendations for schools. So we recommended that the SDA slightly reduce the foot candle requirements, which would also reduce the amount of, amount of illuminance that LEDs would need to be set at in the classrooms. We looked at optimizing daylighting and shading, and I know that Dan's going to be talking about the daylight dispersion panels that we were ultimately recommending. There's some fine tuning of the turn off timing of occupancy sensors or vacancy sensors. We also looked at light shelves, although there's some challenges in a city school environment related to the maintenance of light shelves on the inside of a classroom, as well as exterior light shelves that could potentially have ice hazards. So ultimately for this already designed building, based on its setback requirements and its in the site itself, we could not recommend light shelves. And finally, elevator ECMs. This is one unique system. We are recommending a gearless elevator with a regeneration drive. There's some savings that came out of this higher efficiency elevator system. I'll turn it over to Dan now to talk about the envelope.
The envelope was kind of a large package of energy conservation measures. Overall, it represented about 7.7 source CUI reduction for the overall package, which was up there relative to the other packages. There's a number of specific measures here: air tightness, specific upgrades to walls and roofs and different components of the building, upgrading windows. So I'll go through each of these individually. But it's interesting to note that the EY reduction associated with each of these is listed here. The highest impact ones were by far air tightness, followed by using triple glazing, and then thermal bridge mitigation and higher levels of insulation in the walls. So, I mean, those are the passive house principles for enclosures. We've applied them and they work here. So I'm going to show you a series of diagrams that essentially show there's sensitivity analyses that show different levels of each ECM and how effective they are. So this one is air tightness. So on the dot on the upper left represents the kind of base case level of air tightness, and the other dots were other targets that we were looking at. Ultimately, we went with the most stringent approach, which equates with the passive house air tightness per facade area requirement. So you can see here that the kind of dashed circle is around 0.6 air changes per hour, but by using the facade area approach, it was more like 0.22 air changes per hour. So, this included the whole suite of air tightness things that we all talk about in the passive house world, air barrier reviews using better windows and doors, tapes and membranes instead of sealants, and all those things, as well as, kind of installation and testing, training, mock-ups, enclosure commissioning was a specific thing that the School Construction Authority can just specify to help with that. and of course the blower door testing regimen. You know, guarded blower door testing for certain areas during early in construction, and then full blower door testing. Like for the exterior walls and the R value of them, the sensitivity analysis showed that there was reduced effectiveness after about R25 or R30. This is consistent with other projects that we've seen. I mean, it makes sense for a house in Vermont or something to have R40 walls, but in New York, for a building that has relatively high internal heat loads, we don't need that much insulation. On the right, this is kind of a matrix that shows a number of facade assembly materials that we were studying. The School Construction Authority uses a lot of brick cavity wall, also a lot of precast concrete rain screens, precast concrete, and also some metal panel rain screens. So we looked at a whole bunch of things, and there were like a number of assembly methods that can achieve this kind of R value. So here's the assembly. The basic standard wall has about 3 inches of insulation in the cavity. SCA already specifies stainless steel brick ties, so that's good because that's something that we would propose as a lower conductivity tie. And so our recommendation increases the depth of the cavity to the maximum that's available from off-the-shelf components. So it's about a 6.5 inch cavity that allows you about 5 inches of mineral wool in the cavity. And then we supplemented on the inside with a couple more inches of insulation to get up to the R30. For the roof, sensitivity analysis showed around R40 was going to be plenty, and then there was some diminishing returns. Very simple change in this case. SCA already has an inverted membrane roof type assembly. Simply a matter of adding a couple inches of insulation to the top. Similar with below grade, SCA already insulates outside of their foundation walls and sometimes below the slab. So when there's a kindergarten or pre-K or some kind of classroom at the ground floor, they call for 2 inches of XPS insulation currently. Our improvement essentially covered all of this underneath the slab with 3 inches of insulation. So it was good that they already had those measures. It's just a matter of stepping them up a little bit. And in terms of the sensitivity analysis, we found that about R15 was just enough. We didn't have to go further. The sensitivity analysis for the glazing was really interesting because it shows no diminishing returns. So these are high-end, Schuco, whatever, like different manufacturers can definitely do R values, U value of 0.18 or 0.13. There's no diminishing returns there. You can keep going and make windows better and better, and they will continue to perform very well. One thing I'll note too, we ended up selecting the 0.13 U value target. That essentially means triple glazing with 2 low E coatings. The low E coating does help in the cavity to lower the U value. The standard SCA window is arranged with a low hopper and a fixed light above. The hopper is operable. Teachers don't have access to the key. It's really just maintenance people have access to the key, and they're used only in emergencies. So we wanted to make some changes. Well, first of all, the sight lines aren't that great. You can see that horizontal bar is like right in the vision zone. The SCA had done an experiment, some test runs with this other material called the light dispersion panel, which have relatively high R values and bounce light through classrooms. It kind of scatters the light through the room better than shades or lamination materials. So the thought here is to have this higher R value, lower U value light dispersion panel up in kind of a daylight zone, and then leaving the clear glass in a vision zone. And of course, having some operable clear glass lights. So these light dispersion panels, they're available up to like R25 or so for curtain walls. For these kind of windows, they'd max out at around R value of 13, which is still better than even triple glazing. You can see in the kind of cyan color where we're proposing those. So in the gym, for example, where you don't really need a view out, we proposed them there. And then at the upper part of the windows in all the classroom spaces and the cafeteria in this case. We did not propose it around doors or at the ends of corridors where you really do want a view from far back. Also related to glazing, the design has a series of metal panels that are integrated with the glazing system. The base case design has pretty simple, like 1-inch insulated infill panel. We found this other material that it has an R value of 21. So instead of trying to have just a basic 1-inch insulated panel and then trying to insulate inside it to kind of compensate for that, we just use this simple panel and have it integrated with our much better windows. Hopefully something like this can just become standard very soon. And here in purple is how that plays out. Later, I'll be talking about some details. So just one thing to notice here is the length of these window bays. These are some very long window bays that'll come into play later. So then in terms of thermal bridging, like every passive house project, we went around the entire envelope and designed out all the thermal bridges and did all the modeling to prove it. And I'll just talk about some of those examples. Here's the parapet. The SCA does poured in place concrete parapets. They do this for a number of reasons, but that's what we had to design for. So essentially we were talking about the structural thermal break products and just designed those in, pretty easy to do. And in terms of the brick cavity wall, standoff shelf angles with thermal break material behind them was really all we had to do. Those are becoming more and more normal in the market. Other kinds of thermal break materials like the high density polyurethane products that can handle a lot of compressive strength. We use those under dunnage and under brick at the roof and under brick also at the sidewalk. Some of these details, we had extensive conversations with the School Construction Authority. There's some very practical concerns that they deal with on a day-to-day basis in terms of maintenance and repairing buildings that where there's degradation. So they really wanted to make sure that these kind of new approaches would work, and we felt pretty strongly that this kind of thermally broken load-bearing block can work under brick and dunnage in this way. The smoke vent was a big win. We discovered that there were a number of gooseneck air vents above shafts in the standards, and those gooseneck shafts, they're essentially there in case there's a fire, so that you can kind of open up a smoke damper and clear smoke out of the shaft. But we realized that those would be, exactly the kind of air tightness leakage spot that we would have to design out. So we actually consulted with some manufacturers of these products, and we eliminated that whole gooseneck assembly, and instead used a thermally broken smoke hatch, a thermally broken hatch, which also acts as a smoke vent. So these manufacturers, they had thermally broken hatches for access, and they had smoke vents for smoke, but they hadn't combined those two products together yet. But now they are, and this product is now in the market. So it's an R20 thoroughly broken smoke hatch, which now everybody can specify.
Well, and I'd like to add, Dan, too, that the exciting thing about what FX Collaborative did here by going to the manufacturers and really kind of pushing them farther, we were able to also recently been leveraging that early work they did with Bilco and getting some of the other manufacturers aware that this is an issue. And now we have about 3 manufacturers that are saying, in addition to Bilco, that they should have these products ready to roll out this coming fall. So it's kind of an exciting way that this study kind of had a little spin-off of pushing one of the markets farther.
Yeah, and fun to have a client like the School Construction Authority whose weight we could throw around with manufacturers. So just a few more details. Here's the base case window. You can see the masonry sill and the steel head, which are huge thermal bridges. And the way we change that is just like many passive house projects. First of all, the assemblies that I talked about, the triple glazed windows with the better thermal breaks, but then really aligning the window in the insulation zone was quite a challenge. Those long window bays that I was talking about all require movement at the top of the window. The way these buildings are built, the slab to slab movement is taken up at the head of the window. So currently there is no kind of passive house level window that has a head receptor for the window to move up and down in. That's actually airtight. So we spent a lot of time designing that detail. So that this particular solution has some metal frame around the back of the window that facilitates airtightness and movement. But we did suggest to the School Construction Authority that they maybe change that way of building these masonry buildings and use punched windows. If you use a punched window, then you can more easily achieve airtightness by sealing to the back of it with tapes and membranes in more standard ways.
Great, thanks, Dan. So if we've done our job correctly, we've reduced our internal loads. As Dan just went through, we've optimized our envelope system, reduced the thermal bridging. So now we're on to our HVAC system. And we evaluated several different HVAC systems. This first one is an adaptation of what the SCA standard is, which is essentially some rooftop units, those RTUs, that are running chilled water and hot water from a boiler and chilled water from a chiller, and a cooling tower in this scenario, although that is not currently an SCA standard. The cooling tower has a benefit of it increases the efficiency of the cooling system, but then there's other operational issues with the cooling tower and issues related to Legionnaire's disease. So there were a couple of iterations of this system with and without the cooling tower, with modular chillers and modular boilers, etc. And so that's how the water systems move. And then the air moves primarily ventilation, air, and cooling is provided through the RTUs to VAV boxes in classrooms. And there's occupancy sensors in the classrooms, which will vary the amount of outdoor air delivered to a classroom. And then those fin tube radiators are providing the heat for the classroom along the perimeter, the exterior perimeter wall. So that's the SCA standard, and quite honestly, SCA has done a really good job of optimizing the efficiency of this particular system, reducing ventilation rates and fan powers associated with moving air around in the building. But we did investigate some other strategies. Another mechanical system that we investigated was a water source heat pump system. And the water source heat pump system will have also a boiler, but it will have a lower temperature water loop around the building. It would have a dry cooler in this instance that we investigated. And otherwise, there's a central loop throughout the building, a condenser water loop. The condenser water loop connects in the classrooms to individual water source heat pumps for each classroom. So there's something nice about having water source heat pump individual to every classroom. You have a little bit better controllability of your heating and cooling per classroom. And in this scenario, we also investigated individual ventilation, not a central ventilation system like the previous scenario with the rooftop RTUs, but individual ERVs in each classroom. The challenge with that ventilation strategy is where your exterior air comes from. And there are definitely several areas of New York City where you do not want to pull fresh air from the street side. So there's going to be limitations to how often that strategy can be implemented. But certainly a room-by-room ventilation strategy will reduce total fan power, and we noted that, but we decided that for this particular case study, it wasn't a solution that would work. We did investigate a couple of iterations of a VRF, a water source VRF, as well as an air source VRF. And at the end of the day, it seems like with all of the restrictions and with the optimization of the chillers and the boilers, the VAV modular chillers and boilers and essential ERV on the rooftop units was really sort of the most energy efficient way to heat and cool and ventilate this building. So there wasn't too much of a change from the base case scenario to what is being recommended for this particular building. On the next slide, we'll talk about some of the other things that we investigated. We investigated air source VRFs. AC is required in all city schools now, so we have to take that into account. We investigated energy sources, what were the opportunities to electrify, both from a VRF perspective, that's certainly an electrification strategy, but can we take this system with a central boiler and electrify that, and what would that look like? We definitely looked at that. And we also have to consider who is operating these buildings, what are the unions that are operating these buildings, and what are their requirements and skill set. On the next slide, we talk about the components, the individual components related to the distribution, the piping of the HVAC systems. We had the benefit of, like I said, an already designed building. We were able to reduce airflow because of our reduced loads in the building. However, we decided to keep the ductwork at the same size as the original design and not reduce the ductwork and save on that first cost, mostly because oversizing ductwork had a really good EUI savings. We also increased the piping insulation for the distribution of chilled and hot water. There's a night flushing benefit that we could do on the RTUs. There's something to be said about being smart about how the building is being used in partial capacity. So we would have to work with the principal of a school, but in terms of how they would operate the building in partial occupancy in summertime, could they just use the first floor rooms, which might be the coolest in the building, and then turn off the cooling on the upper levels of the school to save on EUI? And there's also some over voltage control that would benefit in reducing energy use. In addition to HVAC, additional HVAC components, we did look at geothermal systems. The original design did investigate geothermal energy piles. However, there wasn't sufficient room or sufficient energy available in the ground to pull and offset the energy use of the building. So it wasn't really feasible for this particular project. We investigated heat recovery from the MDF and IDF rooms, ceiling fans, increasing the distribution of piping insulation, which we applied, and as we said, the zoning. So all of the accepted ECMs were reduced the total source EUI by about 5, which we thought was a success. Related to ventilation, I mentioned as we started out that the RTUs deliver air to classrooms, and outdoor air is controlled by occupancy sensors. That was in the old SCA standard. Just by switching over to a CO2 controlled DCV, we could see significant savings, and that just helps to helps you understand that maybe there's 2 or 3 people in a space, which an occupancy sensor would trigger for full ventilation as if the classroom were fully occupied, whereas a CO2 sensor may say, there might be 3 people in this room, but there's not enough CO2 buildup for me to provide full fresh air. So there could be more variation in airflow. So that coupled with the oversized ductwork that we previously talked about. We did take a look at some other strategies, air cleaning modules. We compared central and decentralized ventilation and also natural ventilation. And there's some limitations to what could happen in this particular building, but it could be further investigated with other schools. Finally, service hot water systems. The biggest ACM related to this system is a low flow aerators, which were about 0.2 GPM applied to the project, and that resulted in the highest savings. Again, related to electrification, we did investigate heat pump water heaters instead of a gas-fired water heater, which has further potential savings. So when you stack all of these packages together, you can see how they interact with each other. We applied the internal loads together first. So up to the elevator package, we were able to reduce from 88.2 down to 72.9, which is a 17 source EUI reduction. The enclosure brings it down another almost 8 EUI, and then the HVAC system and components and ventilation strategies, and along with the service hot water, bring us to 54.2 source EUI. So that's like our final result of 54.2. So you would first think that, man, we didn't reach our goal. The whole point of the study was hopefully to get to 38 kBTU per square foot per year. But we did look at these numbers a little bit differently. If you just take out the commercial kitchen, the rest of the school does achieve the 38 kBTU per square foot goal, which we think is a win, is a success story, as the 38 kBTU per square foot per year was not initially designed for commercial kitchen use.
But just to add that we did speak with PHI about how they would handle something like this, and they definitely agreed that they did not forecast commercial kitchens in schools, and might be amenable to additional EUI for a school like this.
All right, so as you can tell, we studied, then we peer reviewed, and then we studied some more. So it was an exciting time as we were learning about the different measures that we could employ. And some of us were a little impatient too, and we wanted to actually at the SCA kind of move some of these that really look like some quick wins out the door. Because as I said, at any given time, we have 10 to 15 schools in kind of the heart of design. And so as we were learning some of these things from the study, we were saying, well, geez, why couldn't we apply these like no cost measures to those schools that really, as long as it doesn't slow down their design, it doesn't really affect them. So we were able to do some shifts, like the significant one of going from occupancy demand control ventilation is what we had before, switching to CO2 controlled demand ventilation really gave us a win, and it was an extremely nominal cost, really just the cost of the difference between an occupancy controller and a CO2 controller in a new building. Nighttime air flush out was another one. There's no cost, it's just a controlling sequencing change. The lighting levels, again, no costs. We just needed to reprogram them. And we did have definite concerns with our electrical engineers, even though the recommendations that were given were coming from good sources about being able to lower the foot candles in our classrooms and our other spaces. We were careful to say, well, we don't want to have complaints about spaces being too dark. And our schools are not just used for younger kids who have really healthy young eyes, but also at night school is used in a lot of the facilities for adults who might need more bright spaces. So we made sure that the lowering of the foot candle was in the control setting, but the design still was allowing for the 40-foot candles. So if anybody had a complaint about that space, it could be reprogrammed in the control side to up that ability. On the domestic hot water side, we also had a really exciting win, is that we were providing to The lavatories in the bathrooms, 105-degree temperature, and you're allowed to go down to 85-degree temperature for those sinks, and it's still comfortable for people to use. So we picked 90 degrees. We didn't go at the bottom, and it's a no-cost, huge savings. And actually, this is one of those exciting things that we're able to roll into looking at our existing stock of another, the other 1,500 schools that are already there that are currently using 105-degree temperature. We're actually working with DOE to create a program where they go in with their custodial staff and shift the mixing valves down to the 90 degrees and have a very low-cost, low-labor change in an EUI savings. The kitchen plug loads, like the walk-in cooler installation, that was a pretty minor change since we were already doing changes to the slab and things for 4-inch panels, and the demand defrost in the freezers. It's a $400 part to save the energy. So it doesn't save you a ton of EUI, but it's $400, so why not? And then we were able to not just roll that into, those elements into all of our projects that are kind of going through a certain phase of design, but we also said, hey, how can we take what we've learned in this study, because as I think was mentioned early on, this was just a study applied to this building as an example because FX Collaborative's project was already out the door, had been bid, and was in construction. So we couldn't make these exciting changes on that school. But we've had since 4 major buildings, one a very large 308,000 square foot high school that applied a lot of these measures even beyond those that were the kind of the low-hanging fruit. These additional ECMs that we're looking at and that we kind of are piloting on these schools, and a couple have already been awarded bid and are waiting for the COVID release of work so that we can get back to getting those built. But the upgrade roof insulation, the under slab, the improved air sealing, in which that really included for us beefing up our building envelope commissioning and really making sure that we had a lot more check-ins at the design side, because even though architects and engineers know to do airtight detailing, if you don't actually do that sort of building envelope commissioning plan in your drawings, then you can't expect the contractor to figure those things out. So a lot of our building envelope commissioning, I would say 80% of it, is really at the design side, helping make sure the details are clear enough that the GC can move forward with them. And on the mechanical, doing the double pipe insulation, that was a relatively low cost change that we were able to implement. The variable speed compressors, as Paula was mentioning, were a relatively simple shift keeping the systems that the GCs on our projects were already used to, just making them variable speed instead of stage compressors was very helpful. And then we are switching for both the domestic hot water and our kitchen, moving away from fossil fuels. And so this standard has been changed now we're only doing heat pump hot water for the domestic hot water for the building, and we're doing all electric cooking for our kitchen. So we've gotten the gas systems out of our new schools on those, which is great. And then now with the local law 94, the sustainable roofing zone, we're doing PV on all of our new buildings where it makes sense, green roofs where PV is not viable. We didn't just stop at the new buildings. So this is where, our excitement was boiling over, and we said, well, we've got all these existing building projects too. SEA does about 300 capital improvement projects a year of various sizes on all of that 1,500 building, school building stock that's already built. And so a lot of these measures, even though it wasn't part of the study and part of the design, a lot of these measures are applicable to existing retrofit work with some minor tweaks. And so we have 3 existing building pilots that were needing new envelopes, new skin. And so there was an overclad process already in place that was going to go to code level. And so we've now bumped that up to this high performance envelope. In addition to that, something that's in the works is to try to add to these schools mechanical ventilation too. So these are old boiler schools that use, quote unquote, natural ventilation in the space. You open the window. But that's something that we were concerned about as we make a more airtight, beautifully wrapped new envelope around these old buildings, and we've got an old natural ventilation and boiler system, how do we feel comfortable that they're getting enough air movement in those spaces? And so you can open the windows and you'll get that air, and they do that. It's just, it destroys your energy efficiency. So we're working on getting additional funding from the city to start doing some pilots on these three to add mechanical ventilation as well. This building, I mean, this slide, you guys can look at in a little more detail on your own. It's pretty dense. It's really, in one sentence, it's showing that when we do envelope commissioning and commissioning of the building, we were able to take that net zero building that was not performing net zero when it first started and was occupied, and within 12 months through the commissioning process, drastically, in that dash red line, reduce the energy consumption. And so where we're pushing things now is to, and it's not just us, it's actually where we're moving with the push, is to look at beneficial electrification. So going fossil fuel free, and I'm specifically saying beneficial electrification because we don't want to just electrify. You know, some of the first thought of when we were being pushed with the gas service moratoriums that happened in this last year, a lot of the thought was, okay, well, we like boilers, maybe we do electric boilers, but electric boilers is straight resistance heating, and they are incredibly energy inefficient. However, they get rid of your fossil fuels, and so they help on the one side to lower your emissions, but it's not lowering your carbon, and it's really not helping in a lot of other ways. It's definitely making your bills increase. So we were able to, working through different types of systems where we can go all electric, and the three main ones are like using our typical rooftop units, which we like for distributing air, but shifting over to rooftop units with heat pump systems, kind of VRF heat pump systems packaged with them to provide that. There's also heat pump modular chillers. We're already doing modular chillers for cooling, but now we can apply the heat pump technology to that. So we do heating and cooling with those modular chillers, and then get rid of the boilers, the gas boilers that would be feeding during the heating season. And then distributed VRF systems is also part of the study. And so we have 3 new schools, in addition to those other ones I was already talking about, that are applying some of those all electric standards because of the gas moratorium. And we're learning from those, and we're hoping that in the future we can come up with a solution that we really think is kind of a win-win with the all electric buildings, and that will not only reduce carbon and emissions, but also be a much lower EUI as well. So that's kind of helping the local law 31 requirement as well as the local law 97 carbon reduction requirement. So these are all of the really exciting things that just this one study kind of helped generate that interest and that understanding of these kind of 75 energy conservation measures that FX Collaborative and Stephen Winter and the rest of the team highlighted and identified that we could start to apply in our schools. And so we have a lot of challenges ahead, some of which I already mentioned, but we're working on creating a master plan so that we can achieve the 2050 goals of the city. And they're very aggressive goals. We have a lot of different ideas of how to get there, and we're actively working on that. We have 2 deep energy retrofits that the mayor's announced that need to be done by 2025. And so we're working on taking projects that will get to that level by 2025. And then also, you know, as mentioned before with the plug loads, once we really saw how large these plug loads are for our energy consumption and carbon emissions, we are currently working on a study and having some early results showing that maybe we can actually, just by specifying specific equipment for their energy consumption values, which it currently isn't in our current procurement process as something to consider, we might be able to lower anywhere from 10 to 12% of our total plug loads just by not necessarily even changing the cost, but just changing the spec of that equipment to actually include energy efficiency as a requirement. Well, thank you very much. We appreciate your time.